Welcome to Study Loop.
Okay, everyone, let's begin solving problem 38. So before that, let's set it up. So the basic physics picture of this problem is we have an aperture and we have rays pass through this aperture. And after that, in the aperture, we have a screen there, and the distance between the aperture and the screen S is 1.2 meter. The rays comes through this aperture and it will form some pattern there. That's what we call the airy disk. Let's draw it. So something like this. At the center, we have a central maxima, which is called the airy disk. And along with it, we have the first the dark rings. Oh, that's a little bit harder to draw. Yes. And outside of the first dark ring, we have the first bright ring like this. And then we have the second dark ring. Let's set that. So if we draw it on the screen on the left side here, we will have the airy disk like this, and the first dark ring, something like this, and the first bright, and the second dark like this. Here is what it is also what we have. So what you learn, the distance on the screen between the first dark ring and the second one is delta y equals 1.65 millimeter, which is also 1.65 times 10 to minus 3 meters. And if we complete this plot, you have that. Central. It's a little bit ugly, but whatever, it doesn't affect our calculation. So the first angle, what we call theta 1, is the angle according to the position of the first dark ring, and the second one, theta 2, is the angle, or say the angular position of the second dark ring there. So the position, I say the angular position given by the equation 36, 18, and 17, the theta 1 equals 1.22 times the wavelength lambda over d, and d is the diameter of our aperture here, and theta 2, which is the angular position of the second dark ring, equals 2.23 lambda over d. And along with it, we already learned that lambda equals 490 nanometers, which is also 490 times 10 to minus 9 meters. So basically that's all for this problem. So let's go to calculate and find out the relation between all those numbers. So as what I said just now, we have the two angles like this. Remember that this is delta y, This is theta 1, and this is theta 2. So what's delta y here? This distance is s. So delta y is the distance s times tangent theta 2 minus distance s times tangent theta 1. So this is our delta y. So from this, we find the relation between the theta 1 and theta 2, and along with the two equations, sin theta 1 equals 1.22 lambda over d, sin theta 2 equals 2.23 lambda over d. So those are three equations. What do we get? We don't know theta 1, we don't know theta 2, and we don't know the diameter d there. And we have in total three equations. So which means we can solve those together and get all those parameters we didn't know yet. So let me basically introduce one tricks. So because the theta here is really relatively so small, so we can use the approximation about the theta, the sine theta, and the tangent theta. So what we'll get is this one is approximately also equals to tangent theta 1. And similar on the theta 2 here, it's approximately equals tangent theta 2 here. So what we need is just plug in the tangent theta 1 here and the tangent theta 2 here. And we are learned that s equals 1.2 meters. So, and we learned delta y equals 1.65 times 10 to minus 10. It equals 1.2 times 1.22 lambda over d minus 1.2. Oh, I'm sorry, I got it wrong. There should be the 2.23, not 1.22. And here is 1.22. This is the term about theta 1. So now it looks like much more easier for calculation. So the only one is we didn't know in this equation is the diameter d here, because we already learned that lambda equals 490 times 10 to minus 10 meters. So we just plugged it in here. And finally, we will get our diameter equals 0.3 and 3 6 oops. Let me write it down. 0.036 unit in meters, and it equals 3.6 meters. Let me write it down here. Millimeter. Yeah, this is much more easier for write it down relatively shorter. Okay, thank you.